Hi, this is Chris Jobling, and this is a short video to introduce the case study that's in NICE for the Modern Control Systems course. This first diagram here is the antenna azimuth position control system. You can see we're trying to control the azimuth, which is the angle I believe that the antenna here makes with the horizontal. By using this setup here where we have a large motor, a number of gears, and we're measuring the azimuth, this angle here, by means of a potentiometer, which gives us a voltage proportional to position. And on the input side we have a potentiometer which we're using to specify the desired position of the antenna, and that's fed into a differential amplifier, power amplifier, which drives the motor. And the idea is that when the angle here equals the angle here, the power from the differential amplifier disappears and the motor comes to rest. So relatively straightforward. If you look at the schematic diagram, this is what you end up with. There's a potentiometer, there's the amplifier, there's a power amplifier, there's the motor, a model of the motor here with a resistance, armature resistance coming in. There's the motor there. These are the parameters on the motor: the torque, the damping, the various gains. Here's a fixed field for the motor. Then that's fed through a gearbox through the load, which represents the azimuth of the antenna itself. And here we've got some damping in addition. And here's a feedback taking off another gear from potentiometer to give us the voltage proportional to position, and that's fed into the amplifier. And when these two inputs are zero, then the whole system comes to rest. And this is a block diagram of the system. Here you can see that the various transfer functions are put together, and there's potentiometer, there's a preamplifier, there's preamplifier, motor and load, gearbox, and the angle coming off. Then that's fed through the potentiometer, fed through a summing point, which is our representation of the differential amplifier here, and the potentiometer signal here, two voltages here compared, giving us what's called an error signal, which drives the system to rest. And here we have a number of the different parameters depending on which sort of configuration we wish to use in our system. And then for various problems that come later in the case studies, there are a number of parameters which need to be calculated and worked out. You could easily build this model in Simulink just using transfer function models and the various parameters, and I would urge you to perhaps do that. For the purposes of the case study, what I'd like you to do is get hold of the outline and just read through the first part of it, which starts here on page 12. Just read through that. This basically tells you how the model has been set up and the various responses you'd expect to get from it, and give you a bit of insight into the physical parameters. And then the first next part I'd like you to read is from page 94, which goes through the modelling and specifies how those models were achieved, what assumptions have been made, and so on, and how we come up with a transfer function for the system. If you like a challenge, you can go on to look at this other example, which is a more nonlinear system, and it's similar perhaps to the case study we're going to do later on. This is a model of a human leg, and then we've got a challenge problem here where we want you to model another system. So have a look at the case study, read through that, and help to amplify what we covered in the lecture today.